void state, its potential energy, damage potential, it's equal to 0. So does it have any meaning, or it's simply you have to start from the maxima of that?
Well, the absolute value of the potential has no significance.
Okay, so if there are no more questions, I now invite Professor Shankar to give a memento to our distinguished speaker, and thanks speaker again.
Thank you.
So before we leave, I need to say a vote of thanks to several people who have made this solution possible and representative. I'd like to first thank Professor Subramanian again for very kindly accepting our invitation and giving us some excellent talk. I'd like to thank Professor Ganesh, who is not here, all volunteers, the Media Lab, and all of those who have helped in various ways to make this a success. And lastly, I'd like to thank all of you, the audience, for enjoying this talk. Okay. Thank you.
Is it blurred?
Say 1 minute, I'll introduce you for a minute before we...
No.
I just say it's part of the CVS distinguished lecture that he was...
Okay. Okay, thank you, Shankar. So I'm going to be talking about the role of the continuous spectrum in hydrodynamic stability. So we'll get to what the continuous spectrum is. Okay. So the initial part of the talk is about the discrete spectrum, okay, the normal spectrum that we encounter in stability, and then we'll see why we need the continuous spectrum and the role that it plays. Okay. So first I'll introduce, so the spectrum relates to the eigenvalues of a differential equation, okay, a boundary value problem. So we'll first consider a simple eigenvalue problem that belongs to a classical paradigm, which is called the Sturm-Liouville theory. So I'll just introduce a simple example, which is a vibrating string, and the vibration frequencies are the eigenvalues in that case. And then after summarizing what it is like in the Sturm-Liouville paradigm, we'll go to the case of interest, which is hydrodynamic stability. And what I'll be talking about is inviscid hydrodynamic stability, which means that the viscosity is negligible. So in other words, the Reynolds is infinity. And we'll see that the governing differential equations for the modes of an inviscid fluid is the Rayleigh equation. Okay? And then after looking at the Rayleigh equation, we will first analyze what the discrete spectrum of the Rayleigh equation is, which means that the modes of the Rayleigh equation that look like the modes of the classical paradigm. Okay? And then we will go to what is the continuous spectrum of the Rayleigh equation, because that is more important in some sense. Okay? And because this is pedagogical lecture, we will actually derive the form of the continuous spectrum in a couple of simple problems. Okay? So we look at the simplest case, Couette flow, and then we look at pipe flow, and we look at two-dimensional perturbations, which are simple enough that you can find the continuous spectrum. And then given, I mean, depending on the time, we will go to problems of a greater complexity. Okay? Okay, so this is the vibrating string problem. U there is the amplitude of vibration, and U satisfies the wave equation. C is the wave speed, which is related to the tension in the string and its mass per unit length. Okay? But right now, what we care is we have a differential PD like this, and with suitable boundary conditions. These are just fixed end boundary conditions. So the vertical displacement of the string is 0 at the ends. So it's fixed at the ends. Okay. And we have certain initial conditions. The initial conditions involves both specifying the displacement, how much I pull the string, and the velocity of the string at the initial instant. Okay. So knowing this, I have a well-posed problem. Okay. So I'm going to look for normal modes of these the vibrating string, means characteristic oscillations that preserve their shape even as they oscillate in time. Okay. And these oscillations, though they are function of both the position x and time t, they exhibit a separable dependence on x and t. So we write that it's a function of x and a function of t, and this function of t is a complex exponential. Okay, so that denotes an oscillatory function of time. Okay, so c lambda is the frequency, lambda here is like the wave number. Okay. So if we just substitute this in this equation, we get a simple second order differential equation in x, okay, and we get x to be sinusoids. Okay, and the wavelength of the sinusoid is dependent on that parameter n. Okay, so the wavelength is the reciprocal of n by L. So it will be higher the value of n, smaller is the wavelength of the oscillation, higher will be the frequency. Okay, so we have these elementary modes. That's the fundamental mode. That's the first overtone, the second overtone, and so on. Okay, and n is any natural number. So there are a countable infinity of such modes. Okay, and the important thing is that because we have an infinity of such modes, we can combine these modes to represent an arbitrary disturbance of the string. Okay, so we pull the string in an arbitrary amplitude profile. I can decompose that amplitude in terms of this basis. Okay, since these are the sine functions, that is equivalent to expanding the amplitude in a Fourier sine series. Okay, and once I know the individual modes, modal amplitude, so basically what I'm saying is I have an initial amplitude u of x. I am going to just write it in terms of okay, and these are the unknowns, but knowing this function, this is just a Fourier sine series, those are the coefficients, so I can immediately invert it in terms of u naught. So I can find out ans. Okay, once I find all the ans for all n, then I know what is the projection of u naught on each of the elementary modes of vibration of the string. Okay, once I know this, then I know what is the initial decomposition, the decomposition of the initial amplitude in terms of the elementary modes. Then it's trivial to get u at any finite time, because all I have to do is okay, so I have to just oscillate each of these modes at that frequency. I immediately obtain the finite time solution from the initial disturbance. Okay, so this is the advantage of knowing the modes, because once you project an arbitrary function in terms of the modes, an initial disturbance, you immediately know the solution for any time, because you know how each mode behaves for all times. Okay, so the idea is to try and do this in the context of hydrodynamic stability. Okay, so this is what is called a discrete spectrum, because as you can see, the eigenvalues are well separated. Okay, and they form a countably infinite set, and we'll see that this is usually not the case in hydrodynamic stability. Okay. Okay, so we'll go to hydrodynamic stability. What I've written down is the equation governing the vorticity field. Okay, so that is the convection of the vorticity field. That's the vortex stretching term, and this is the diffusion of vorticity. Okay, so we are going to look at small amplitude disturbances to a fluid. So what we'll do is we'll say that the velocity field is made up of a base state profile plus a small disturbance, and likewise for the vorticity profile field. Okay, then we substitute this, and because these disturbances are small, we neglect the quadratic terms and retain only the terms that are linear in u prime and omega prime, and we get this equation. Okay. And remember, we are dealing with inviscid stability. Inviscid stability corresponds to Reynolds going to infinity, and so I will push out that term. I will only consider the inviscid vorticity dynamics. Okay. So that is the equation that is going to underlie all of what I say today. Okay. And so just to identify the different terms, this is just the unsteady term, the variation of the perturbation vorticity field with time. This is the convection of the base state vorticity by the perturbation velocity field. The opposite, convection of perturbation vorticity field by base state, and these are the two vortex stretching terms. Okay, so the perturbation vorticity is stretched by the base state gradient, and the base state vorticity is stretched by the perturbation gradient. Okay, so we are going to go in this sequence. We are going to first consider planar shearing flows, and the two examples are Couette flow, where u of y is just y. Okay, it's proportional, a linear profile, and if time permits, we will go to consider a channel flow, where u of y is a quadratic function of y, and we will start with two-dimensional perturbations. Okay, the advantage of two-dimensional perturbations is, in this case, there is no dependence on the third coordinate z. So x y is the plane of the flow, u is in the x direction, y is perpendicular to the flow direction, and z is along the base state vorticity direction. So two dimensions means that there is no dependence on z, and if there is no dependence on z, the vortex stretching terms in the equations I just showed would be identically 0. So it allows for a simpler equation. But we will also consider pipe flows, and in pipe flows, the analog of two-dimensional perturbations are axisymmetric perturbations. Okay? So pipe flow is a cylindrical coordinate system. The flow is in the z direction. It varies as a function of the radial coordinate, and the analog of two-dimensionality is that there is no variation with theta. Okay? So it is axisymmetric. But the crucial difference is that while there is no vortex stretching in the planar shearing flow case, there will be vortex stretching here, and that leads to a crucial difference. Okay? So I am going to go in this sequence. Okay? I will first consider linear flow, linear planar shearing flow, two-dimensional perturbations. Then I will go to actually pi-Poiseuille flow, axisymmetric perturbations, and then come back here to consider a nonlinear flow, and then go to non-Poiseuille flows depending on the time constraint. So that is roughly in increasing order of difficulty. Yeah. Okay. So right. So for two-dimensional flows, like I said, there is no vortex stretching. So there is only the unsteady term and the convection of the vorticity. Okay. So here, this is the material derivative of the vorticity field. Okay. And this term arises because the base state vorticity is not constant. Okay. So this is convection of the inhomogeneous base state vorticity field by the perturbation velocity. Okay. So what I do again is similar to the string problem. I say that I am going to look for normal modes. Okay, so remember, there we again had a complex exponential. So we are going to do the same thing, expand both the vorticity field. The vorticity field now has only one component. It is a two-dimensional perturbation. A two-dimensional flow only has a vorticity pointing out of the plane. So that is the only component of vorticity. Okay. So I am going to expand it as a wave. This wave propagates in the x direction with velocity with speed c, and the wave number is k. Okay. So this dependence on y has to be found. Okay. Now similarly, I expand the normal velocity y in the perpendicular direction. So that is y. There will be a corresponding velocity in the x direction that can be derived from the continuity equation. Okay. So when you substitute this into the Rayleigh equation, you get this equation. Okay. So you just, it's, I'll just write it down. Okay, so this is just the convection of, sorry. This whole thing is the vorticity. Okay, so I'll just show you that. So that term there, that operator, that is proportional to the vorticity, and it's easy to see that because you start from the definition of the vorticity, which is and because you have assumed wave-like perturbations, it's going to be Ikx okay, it's going to be proportional to this, and then you use the continuity equation. The continuity equation is okay, so you get the Ux is and then you substitute it here so that you get Ikx so you get that omega z is actually proportional to that quantity. Okay. So that there is the perturbation velocity, vorticity, that is the wave speed, okay, that constitutes the unsteady term. That's the convection of the base state vorticity by the flow, okay, and that's what is known as the induction term. Remember, the induction term is the convection of the base state vorticity by the perturbation velocity field. Okay, so the base state vorticity is in general not a constant. Z is the base state vorticity, dz is the gradient of the base state vorticity with y. Okay, so it exists because the normal velocity converts more vorticity into a given region and less vorticity out of it, and that leads to this source term. Okay, so then this is the eigenvalue problem to be solved. Okay, the eigenvalue problem is in the normal velocity. We have a second order differential equation here, and we have the boundary conditions. We can take the boundaries at y equals 0 and y equals 1, okay, and uy will be 0 there. Okay, so we have to solve this and get the characteristic eigenvalues, which are the values of C. Okay. Right, and once we know uy, the vorticity field can always be obtained from this. Okay. So now first we look at simple cases. Okay, the simple cases are where the Rayleigh equation has a discrete spectrum. So we'll first look at the discrete spectrum of the Rayleigh equation and see the difference between the discrete spectrum of the Rayleigh equation and the discrete spectrum for the vibrating string. Okay. So in order to see the discrete spectrum, we will consider the simplest instability problem of a homogeneous incompressible fluid, which is known as the Kelvin-Helmholtz instability. Okay. So the instability is that of a vortex sheet. Okay. So you have a sheet and the vorticity is only non-zero on this sheet. So you can imagine this sheet being threaded by vortex lines. Okay. And we will analyze the instability of this vortex sheet to perturbations. In other words, we will imagine this sheet to be slightly disturbed and see how that disturbance amplitude evolves. Okay. Now the first question to ask is, what does the base state vorticity profile look like? Well, the base state vorticity is only non-zero at this y location. It's 0 everywhere else. So the vorticity is actually a delta function. Okay. What is the velocity that it induces? It induces a discontinuous velocity field with a step jump, and that is because each of these vortex lines wants to induce a circulation like this. So you can imagine, if I look at the sheet along that direction, the vortex lines are all pointing towards me. These are the vortex lines making up the infinite sheet. So it goes on to infinity in both directions. Each vortex line induces a circulation like this, okay? And when you add up all these circulations, you can see that the fluid will be moving in that direction above and in the opposite direction below, okay? So if you add a uniform velocity to this, that will give you a stepped velocity profile. So that's the base state profile that we are analyzing the stability of, okay? Yeah, I have just reversed it for convenience, yeah. Okay, so now we perturb the vortex sheet, okay, and analyze the instability. Now this instability can be easily seen physically. Okay, so we had the initial plane vortex sheet here, and remember the velocity field it induced was this. So I'm just going to take it the other way, okay, so because it's like that in the slide, so I'll just reverse the, so this is the base state velocity profile. This was the original plane vortex sheet, and now I imagine I introduce a modulation, okay, so it becomes a wavy vortex sheet, okay. So now what happens? Well, if I imagine this part of the vortex sheet is now subjected to this flow, so whatever parts of the vortex sheet are going to be in the upper half are going to be convected by that flow towards the right. The deformed parts which are in the lower half are going to be convected towards the left, okay. And now remember, since I changed the sign of the vorticity, the vortex lines are now pointing inward. So I'm going to denote them as crosses. So these were the original vortex lines that were threading the vortex sheet. And now I have these crosses moving towards this point, these crosses moving towards this point. So I have an excess cross vorticity there, okay. And that excess cross vorticity is going to induce a circulation like that, okay. And I'm going to have a deficit cross vorticity here, which is going to lead, because the vorticity is moving away from there, okay. So that's negative perturbation vorticity. That's going to lead to the opposite circulation. So you can see that the induced velocity field due to the deformed vortex sheet pushes this part up, that part down, and again it pushes this part up. So a wavy perturbation tends to amplify, okay. So the vorticities tend to concentrate and rarefy and alternate nodes, and that tends to amplify the vortex sheet, okay. So this is really what's known as the Kelvin-Helmholtz instability, okay. So that there I've shown the vortex sheet amplifying with time, okay. Now if you ask for what is the growth rate of this vortex sheet, so what's the value of, so let's go back to the form of the normal modes. So C when real is a wave speed, the imaginary part of the C is growth rate, okay. So now if we ask what rate does the vortex sheet grow, you can see that the velocity field induced is symmetric. So we expect the vortex sheet to remain stationary but grow. So the wave speed is 0 and there will be a growth rate. So C will be purely imaginary. Now C has units of a velocity. And dimensionally, so if we look at what are the physical parameters that we can use to form C, there is no length scale in the problem, right? The vortex sheet has a 0 thickness. The only parameter in the problem is the velocity of the base state, okay? And therefore, Ci has to be proportional to u. It turns out that the constant of proportionality is half. But even without that, you could say that Ci must be u because there is simply no other dimensional quantity to make a dimensionless function, okay? Now, if Ci is u, then the frequency, the actual growth rate is u times k. Okay? K is here is the wave number. It's the inverse of the wavelength. So what this tells you is that the growth rate becomes stronger and stronger as the perturbations are smaller and smaller wavelength. Okay? And that's because the growth occurs because of convection of vorticity over a distance of a wavelength. So if you have a smaller wavelength, it will take a shorter time for that flow to convect and for the vortex sheet to grow. Okay? So if you in this approximation, the smallest wavelengths grow the most rapidly, and if I plot that Ci versus K versus the wave number, this is a plot of the dispersion relation. Okay? Then I have the growing mode. Remember, this is just half u, and they'll always growing and decaying modes in the Rayleigh equation occur in pairs. So for every growing mode, there will be a decaying mode, and I'll have a decaying mode at minus half. Okay? And remember again, they are independent of K, so they are just horizontal lines. Okay? So now what we'll do is we'll just smoothen the velocity field a little bit. So we had a jump in the velocity field, now we'll make it continuous. Okay, so that's the next thing. So originally our vorticity field was a delta function, and now the vorticity is 0 here because the velocity is constant, and it's constant here. So we have made it, regularized it from a delta function to a step function. Okay, so the vorticity field corresponding to this velocity field looks just like so there is just a plateau of vorticity in a region of height h. So the important thing we have attained by regularizing this velocity field is that we have introduced a length scale in the problem. Okay, the length scale over which the velocity varies from u to minus u. Okay, so you can already see that for sufficiently large wavelength perturbations, which are much larger than h, this length scale is negligible. Things will reduce to the earlier problem. Okay, so for sufficiently large wavelength perturbations which correspond to very small k, we will still have the original problem. But here we have a non-trivial relation. So we can remember, to just take you back a couple of slides, here we could right away say that Ci would be proportional to u, because there is simply not enough parameters to form another dimensionless function. Okay? But now that we have introduced a length scale, we have h, and k times h is a dimensionless wave number. Okay? So f of kh is a dimensionless function, u has the dimensions of velocity, so c here must be proportional to u times this dimensionless function, and I will get that dimensionless function only on solving the Rayleigh equation. Okay? And we expect, because long wavelength perturbations would still behave in the same manner, perturbations with wavelength much greater than h, we expect f of kh to approach half the value that we saw earlier when kh goes to 0. Okay? Okay. Now we are not going to solve this in detail because it's easy to see what happens. Okay? So for this, you have to imagine that we have a non-zero vorticity portion here, 0 vorticity, 0 vorticity. So we can regard the base state velocity profile as consisting of two vorticity interfaces. Okay? That's the first interface between a region of non-zero vorticity and a region of 0 vorticity. The second vorticity interface between non-zero and 0 vorticity regions. Okay? So which means that there are 2 degrees of freedom now. Earlier we had just 1 degree of freedom, which was the vortex sheet. Now there are 2 interfaces that can in principle behave independently. So what we could do first is to consider just one of these vorticity interfaces. What happens if I perturb one of these vorticity interfaces? So this is what it looks like. Okay? It's a perturbed vorticity interface. Now what the signs here denote the signs of the perturbation vorticity. Okay? So how do I get the signs? Remember, the vorticity here is negative. Okay? So this is a negative vorticity region. So whenever I have the interface dipping into the negative vorticity region, I have brought in 0 vorticity into the negative vorticity region. So that is a positive perturbation vorticity. It's greater than the original negative value. Conversely, if the interface moves above, I would have introduced negative vorticity from this region on top of the interface. So I have negative perturbation vorticity, positive, negative, positive, and so on. Okay? So now that I have marked the signs of these vortices, I can simplistically imagine each of them to be an isolated point vortex. Okay? So a negative vorticity implies, remember, a clockwise circulation. A positive is anti-clockwise. So I can replace this by the sense of their circulation. So, this induces a clockwise, anti-clockwise, clockwise, anti-clockwise. And now I look at each vortex here will convect with the sum of the velocities induced by all the other vortices. Okay. So, if I look at this vortex, okay, so let me just draw this. So, I have negative, positive, okay. So, if I look at the velocity say induced by this, okay, this vortex will have a circulatory motion, will tend to push it in this direction. The circulatory motion due to this vortex will tend to push it in that direction. Similarly, this will push it by a smaller amount in this direction, that will push it in this direction. So, you can see that the alternating signs are convecting it such that the convection in the vertical direction cancels, but there is a net convection in the horizontal direction, and therefore, that system of point vortices will actually move towards the left, okay, which tells you that that perturbed vorticity interface, if it were by itself, will move towards the left. Okay. Now, by the same argument, you can say that this vorticity interface will move towards the right. Okay. So, now what does this tell us? Well, we can consider the limit where those vorticity interfaces do not interact with each other, and that limit is where kh is much greater than 1. What does that limit mean? This means k is much larger than h, so that wavelength of that perturbation is much smaller than the distance between the two interfaces. Okay. Now, the influence of this waviness extends till a distance of order 1 wavelength. Okay. So, this wavy perturbation will induce a velocity field which will decay in a distance of order 1 wavelength, and if the distance between the two interfaces is much greater than a wavelength, then the two interfaces do not see each other, they more or less behave independently, and each one is a neutrally stable mode. With this propagates towards the left, that propagates towards the right. Okay. So, we have two neutral propagating modes when kh is much greater than 1. Okay. But there are two things that happen when kh starts decreasing. One thing is actually these interfaces propagate faster. Okay. And the other thing that happens, which you would have guessed, is that their range of influence extends. As they become longer and longer wavelength, their velocity field influence increases, and the two vorticity interfaces are increasingly coupled. Okay. So, at a certain point, what happens is that they are coupled strong enough that there is a resonant interaction between these two vorticity interfaces, and that is when the growth begins. Okay. So, there will be a critical value of kh, which is an order 1 number. Okay. Remember, that is dimensionless, below which longer wavelength vorticity interface perturbations will grow exponentially. Okay. And when the wavelength becomes very, very long, it will reduce to our earlier Kelvin-Helmholtz problem. Okay. So, if you look at the spectrum, then it looks this way. So, here I have two things. I have the imaginary part of c, which is the growth rate, and the real part of c, which is the wave speed. Okay. So, these are being plotted against kh. So, at very large kh, the growth rate is identically 0. Okay, remember, they were neutrally propagating modes. We have a pair of wave speeds. One is propagating towards the left, the other is propagating towards the right. As kh decreases, okay, they become strongly coupled, that they propagate at the same speed, which by symmetry is 0, because the velocity profile points towards the right and towards the left with the same magnitude. Below a certain kh, it is 0, and the growth rate takes off and asymptotes to a finite value as the wavelength becomes infinity. Okay. So, in the limit kh goes to 0, you have a very long wavelength instability, which is in fact the same growth rate that we found in the first problem. That growth rate there is plus or minus u by 2, okay, the Kelvin-Helmholtz growth rate. Okay. So, one more step. So, this is the spectrum. Our velocity profile is still artificial in that it has a kink there. There is a jump in slope. So, for this kinked velocity profile, we just saw the spectrum. Okay. Long wavelength growth rate and short wavelength neutral propagating modes. Now the question is, what happens when I smooth out these kinks, convert them into regions of sharp curvature? It turns out that I retain the growing and the decaying modes, these two modes, but the neutrally propagating mode disappears. Okay? So the spectrum for a velocity profile like that, with which is perfectly smooth, looks like that. Okay? So this is important because the spectrum tells us that beyond this critical wave number, there are no modes. Okay? And below that critical wave number, there is a pair of modes. Okay? And those pair of modes have to do with the maximum in vorticity. Remember, this velocity profile, this piecewise linear velocity profile, corresponds to a step function in the vorticity. Okay? If I smoothen that velocity profile like this, it's going to lead to a Gaussian-like profile in the vorticity. So a smooth maximum in the vorticity. Okay? So the two modes that we are seeing here, the growing and decaying, are associated with that vorticity maximum. Okay? And the vorticity maximum here leads to an inflection point in the velocity profile. So you need an inflection point corresponding to a vorticity maximum in order to see an instability. Okay? But the important thing here is that, again, beyond a critical wave number or below a certain wavelength, there are no modes. Okay? So in general, the spectrum of discrete spectrum of the Rayleigh equation looks like this. So if we have a velocity profile with multiple inflection points, corresponding to each inflection point, there arise a pair of modes as the wave number decreases, as we go to longer and longer wavelengths. Okay? But there will always be an infinite wave number range over which there are simply no modes. So here, for instance, depending on the wave number I look at, if I look at this particular wave number, there are two discrete modes. If I look at this wave number, there's 1, 2, 3, 4 discrete modes. Okay? Of course, this wave number, 0. And this is for a velocity profile with inflection points. If I have a non-inflectional velocity profile, channel flow, Poisson flow being an example, there are no discrete modes. Okay? And so there are profound differences from the case of the vibrating string. Okay? So this is just summarizing it. For an inflection velocity profile, we have a finite number of discrete modes which generally occur in pairs. For a non-inflectional velocity profile, there are no discrete modes. Okay? Now remember, for the vibrating string, we had an infinite number of discrete modes. Okay? And of course, you need an infinite number to reproduce an arbitrary initial condition. Okay? So the question here is, if we only have a finite number or none at all, if we start with a particular initial condition, how do we evolve it? Okay? What are the basis modes or the fundamental oscillations, fundamental vorticity fields for this inviscid fluid? Okay? That's the problem. So it turns out in an obvious manner, because they are finite or 0, that the discrete spectrum is incomplete. The discrete spectrum of the Rayleigh equation is incomplete, and therefore you need something called the continuous spectrum. Okay? And the continuous spectrum, by its nature, tells you that the eigenvalues are not well separated. The eigenvalues corresponding to the continuous spectrum, in fact, form a continuous interval. Okay? All points in a continuous interval are all eigenvalues. Okay? And we will see examples of that. Okay, so this is just a slide telling you the importance. I hope I convince you that Rayleigh. So one thing is that the presence of a continuous spectrum is ubiquitous. In other words, for all inviscid shearing flows, the Rayleigh equation has a continuous spectrum. And it's the discrete spectrum that has very few modes. Okay? Most often just 2. Okay? Of course, it has a fundamental significance because from the point of view of the differential operator, we need to know all the eigenmodes of the operator in order to evolve an initial condition. And it turns out that the discrete and continuous spectra are often intimately coupled. Okay? If you have a continuous spectrum, then you can have the discrete spectrum emerging from that continuous spectrum. So here, this is the continuous spectrum, and these are the discrete modes that pop out of the continuous spectrum. It's also relevant to the laminar turbulent transition. Okay? There is a so-called bypass scenario where you have a free stream with sufficiently large disturbances. for a free stream with sufficiently high level of disturbance, the transition to turbulence doesn't occur via the conventional linear stability scenario, which involves a Tolmin-Schlichting instability. Okay? It occurs via so-called bypass scenario, which involves the continuous spectrum eigenfunctions. Okay? No, actually, good question. This is from the Orr-Sommerfeld equation. Yeah. So that is the viscous continuous spectrum. Okay, so a more mundane reason is that for worrying about the continuous spectrum is that if you use a spectral code, an inviscid spectral code, and solve for any velocity profile, the spectral code spits out all the eigenvalues, and you get patterns like this. Okay, so this is courtesy Shankar's work. And so the theoretical spectrum looks like this straight line. Ci here is the imaginary part of the growth rate. Okay, so you can see that Ci is identically 0. So the actual spectrum is neutrally stable. It's a neutrally stable continuous spectrum. But because there is a continuous spectrum and the eigenfunctions, as we'll see, are very irregular, the numerics is not usually able to resolve it. So it gives you spurious growing and decaying modes. Okay? So in order to understand the structure of these growing and decaying modes, to know that they are spurious, they are related to an underlying continuous spectrum, you need to really understand the structure of the continuous spectrum to be able to interpret the results of a spectral code. Okay? Right. So now we come to the simplest case of the continuous spectrum. So we'll consider just plain Couette flow, where u is just proportional to y. We have a linear velocity field, and we'll consider two-dimensional perturbations. Okay? So in this case, remember, there is no inflection point. Okay? So there are no discrete modes in Couette flow. The spectrum is purely continuous. So we'll try to get that continuous spectrum. And what we'll next do is obtaining the continuous spectrum will allow us to represent an arbitrary initial condition in terms of the continuous spectrum eigenfunction, and therefore to see the evolution of that initial condition with time. Okay, so that we'll do. Okay. So in this case, the Rayleigh equation is very simple. Remember, there was an induction term here proportional to u double prime. Okay, I think I rubbed it off, but the original Rayleigh equation looked like u double prime is of course identically 0 for Couette flow, and therefore we have a simple second order differential operator here. Okay? We have the usual impenetrability boundary condition. Remember, it's inviscid, so I can only set the normal velocity to 0. I don't have the no slip boundary condition. Okay? This is simple to solve. If I equate this operator to 0, I get C1 as just a combination of exponentials. Okay? And if I try to satisfy the boundary condition at y equals 0, I'll have a negative sign. So C1 must be minus C2. And so satisfying one boundary condition will tell me that Uy is okay, it's proportional to sinh, so that when y is 0, Uy is 0. But when y is 1, sinh of k is not 0, okay? And there is no value of combination of those constants that can make that 0, which is another way of saying that there are no discrete modes in this flow. Okay? Okay? So that's no discrete modes, and the spectrum is purely continuous. And this is not only true for Couette flow, it's true for any profile that doesn't contain an inflection point. Okay? So now what do we do? Where do we get the missing modes from? Okay, so to see that, we will again note that, remember, the axial vorticity was related to this operator, second order operator acting on the normal velocity field. Okay. So if I look at the equation, this is really u minus c times omega z equals 0. Okay. And u is just y, so I'm going to write y minus c times omega z equals 0. Now there are two possibilities here. This would imply the first one, which is obvious, is omega z is itself 0, okay, which is what I did. here. I equated this operator alone to 0 and then landed up with no modes. Okay? So this option tells me that there are no discrete spectrum modes. But there is another solution to this equation, and that is that omega z must be a delta function. Okay? So this relies on the identity that x times delta x, where x is the delta x is the Dirac delta function, is actually 0. Okay? So if you have an equation like x power n times f of x, then f of x is actually a1 delta of x plus so on until an delta n minus 1 of x. So the general solution of that equation is the linear combination of the delta function and n minus 1th up to the n minus 1th derivative. This case we have n being 1, and therefore the f of x can be just delta of x. Okay? Now what does delta of x mean? Well, we saw it in the first problem. Remember, in the Kelvin-Helmholtz problem, the base state vorticity was a delta function. That was the vortex sheet. Okay? So here we are finding that the perturbation vorticity is a delta function, which means that the perturbation vorticity eigenfunctions must be vortex sheets. Okay? There is a difference, of course, in that the vortex sheet in the Kelvin-Helmholtz instability had a constant strength everywhere. But this is a wave-like perturbation, so the strength of the vortex sheet must oscillate along the flow direction. Okay? So let's just draw the vortex sheets in the two cases. So that was the base state vortex sheet which we started out from. Okay? This has everywhere the vortex lines have the same sense of rotation. Okay? This doesn't vary in x. Remember, this is the x direction. But now I have a vortex sheet. But remember that the perturbation vorticity field is omega z of y times e raised to ikx. So which means that the strength of the vorticity will change sign after every wavelength. Okay? So I'll have vortex lines here acting to turn it this way. If I go one length away, they'll act to turn it the opposite way, and then again turn it that way. So I must have a discontinuity like that here, like this here, and then again like that here. Okay, but of course I can't have these flows coming in like that. They have to go up, and these flows have to come down. So I can generate a pattern. The pattern what it looks like is this way. Okay, so locally there is still a jump in the tangential velocity. The tangential velocity jump changes sign every wavelength. This is 2 pi by k. Okay? Unlike this, where the tangential velocity remains independent of x, the jump. Okay? So this is the sort of structure that I'm looking at, and this is that vortex sheet with an alternating plus sign and minus sign for the perturbation vorticity. Okay? Okay? Can't hear you. It is valid. There is an no, it will be inclined. It will be the so in this case the wave vector is in the plane of the board. The vorticity points perpendicular to the board. So if you have three-dimensional perturbations, the wave vector will be inclined. The vorticity will point perpendicular to the wave vector. So this wave vortex sheet will be turned through an angle, but it will still be there. Right? The non-modal analysis is essentially a superposition of continuous spectrum modes. So I don't know what your question, so when you say non-modal analysis, what are you thinking of? Well, I will show you that every initial condition can be expressed as a superposition of these modes. So any initial condition can be evolved in terms of these modes, including those that lead to transient growth, if that's what you're worrying about. No. So the very idea of considering normal modes is that there is a simple picture. A normal mode only evolves by propagation. So once I know a normal mode, I know exactly how it will evolve. If I don't have a normal mode structure, it can evolve in a complicated manner. Okay, for instance, here, so let's just spend a couple of minutes. Maybe your question will be answered as I go through this presentation. So why are the eigenfunctions vortex sheets? Okay, why not some other distribution of vorticity which isn't localized at this level? Okay, so now a property of the normal mode is that each structure should be preserved. Okay, the structure should be, it can propagate, the structure can all move with a constant velocity, it can grow in intensity, but the shape of the normal mode cannot change. Okay, now if you have a vorticity that has a finite spread, let us say that it was not a vortex sheet, it was a vortex band in Couette flow, then this band structure won't be preserved because the upper part of the band will be convected faster than the lower part, and very soon it will be heavily distorted. It cannot be a normal mode. Okay? So the only structure that can be a normal mode is that isn't differentially sheared by the Couette flow. For that structure not to be differentially sheared, it has to have a zero thickness. Okay? And the zero thickness vorticity structure is a vortex sheet. Okay? So therefore, only vortex sheets satisfy the criterion of a normal mode. So in that sense, it is not that difficult to guess that the eigenfunctions would be a vortex sheet. Okay? So mathematically, those eigenfunctions are delta functions. Okay? And the important thing is that where is the vortex sheet located? The vortex sheet is located, can be located anywhere in the domain. Okay? If it is located at this y, it is going to propagate with that velocity. If it is going to be located at this, it's going to propagate with this lower velocity. But I can have these eigenmodes located at every possible y in the interior of the domain, and those possible values of y are exactly the continuous spectrum. Okay? The velocity, so if I ask for how fast the vortex sheet will propagate, remember we are talking about the term which is e raised to I k c t. C is exactly the velocity of the base state at the location of the vortex sheet. So the vortex sheet is located at y equals yc. So c is u at yc. And what are the values of yc? Well, yc can vary right from 0 to 1. So which means that c takes on a continuous range of values from 0 to 1. The continuous spectrum of Couette flow is the interval of base state velocities which runs from 0 to 1. Okay? So knowing the vorticity, you can always calculate the normal velocity, because again remember they are related by a second order differential operator. So if the vorticity is a delta function, I really need to find the Green's function for this operator in order to find the normal velocity, and that Green's function is very readily found. I think I had the expression earlier. Okay, so for this operator, we'll just go back a little. So I don't seem to find it, but it can be easily found, and these are the flow fields of the vortex sheet eigenfunction. So this is the vortex sheet that I drew there. Okay, the sign of the sheet alternates in the flow direction. because it's a wave in the flow direction, it's very sinusoidally, and correspondingly you have this streamline pattern. Okay. Here the vortex sheet is located near the center of the domain, but remember that location can vary continuously from one end to the other. So, here is the vortex sheet located towards nearer to the top of the domain. Okay. Okay. So, we have found the vortex sheet. Now, one thing it allows us to do is to evolve an arbitrary initial condition. So, maybe I will go there first. So, before doing that, what I will do is, so remember I considered only the axial vorticity equation, okay, and we just concluded that the axial vorticity was a delta function. Okay. Now, the axial vorticity corresponds to two components of the velocity field, ux and uy. Okay. Within the two-dimensional paradigm, I can also have a uz. Okay. The only constraint is that uz must not vary with z. It can point in the z direction, but it mustn't vary along the z coordinate because I have the constraint of 2 dimensions. Okay. Now, if you write down the equation for uz, it turns out to be exactly the same as the equation for omega z. Okay. So, therefore, with the inclusion of the third component of the velocity field, I have 2 equations, okay, and I have therefore a second family of eigenfunctions. The first family is what we already saw. So, omega z was a delta function, uy is therefore the Green's function. I can derive ux, and uz is identically 0 because this omega z induces a 2-dimensional field. Okay. Now, the second family of eigenfunctions is related to the second equation. Here uz must be a delta function because it satisfies the same equation as omega z, okay, and uy and ux are both 0. So, there is only one component of velocity field that is non-zero, that is a delta function. So, this looks like a jet. Okay. It is a very sharply peaked velocity field at yc. Okay. So, this is the vortex sheet modes. So, here I am showing a vortex sheet at a particular location between the two boundaries, and this would be a sinusoidally oscillating jet. So, that is the z direction there, that is x, and the vertical one is y. Okay. So, this is a jet along the third direction, but it has to vary sinusoidally along the flow direction. Okay. So, we have 2 kinds of eigenfunctions. Okay. Both are singular because both are delta functions. In one case, the vorticity is the delta function, in the other case the velocity is the delta function. Okay. Now, this is of course the reason why the spectral method faces problems because the continuous spectrum eigenfunctions are highly singular, okay, and it is not possible to resolve them using any finite number of Chebyshev polynomials, for instance, and therefore, the spectrum exhibits this ballooning. Okay. Now, we have 2 families of modes. The question is, are they enough? Well, they are enough because you need only 2 components of velocity to be represented. The third component of velocity can be obtained from the continuity equation. So, you have only 2 independent degrees of freedom in an incompressible fluid, and therefore, we can use these modes to represent an arbitrary initial condition. Okay. We will do that. So, here is an arbitrary initial velocity field. So, u naught, there is x, y and z components. Remember, it is 2-dimensional perturbations. So, they are not functions of z, they are only functions of x and y. Okay. And then I write them, each of them as a Fourier integral in terms of their Fourier transforms. So, x here becomes k, I have that Fourier exponential, and these are all the Fourier amplitudes of the 3 velocity components. Okay. So, the x amplitude, y amplitude and the z amplitude. Now, the z amplitude here, I can just write it as this integral over the delta function. Okay. So, this is just an identity because remember, if you look at this integral, use f of yc times delta of y minus yc is f of y. So, I am just using the property of the delta function to write uz naught of yc as uz naught of y. Okay. But what does it physically mean? Remember, these are delta functions along the z direction. Okay. It is a vector delta function pointed in the z direction. So, it is really this eigenmode that I am talking about. This was the z component represented by a delta function. So, these are the second family of eigenmodes, and I have written the z velocity as a superposition over those eigenmodes. Okay, so you can imagine that this superposition is an integral because I have a continuous spectrum. So normally you would write the superposition as f of y is sigma n Cn phi n, where phi n are the discrete spectrum eigenfunctions, Cn are the constants. Okay. Here instead of a discrete index, I have a continuous index which is yc, okay, and I have c of yc times phi of yc. So yc acts as a label for phi, just like n acts as a label for phi in the discrete spectrum case. Okay. In this case, phi of yc is just the delta function. So what I have achieved in writing this trivial mathematical identity is I have written the z component of the velocity field as a superposition over the second family of eigenfunctions. This is written as a superposition of jets. Okay. Okay. So that's one of the three components is written as a superposition of the CS modes, the continuous spectrum modes. Two components remain, but remember I have the continuity equation. So I can use the continuity equation to write ux in terms of uy. So I only have to worry about uy now, the initial uy, okay, that 0 is uy naught is the initial velocity field. Okay. So now I can write uy naught in terms of a Green's function integral of the initial vorticity field. There is only one component of vorticity field, and the normal velocity field is the Green's function convoluted with that vorticity field. Okay. So here one part of my initial condition is written as a superposition of jet modes. The second part I am going there because now I have expressed the second part of the initial condition in terms of the initial axial vorticity field. Okay. And if you recall, the eigenfunctions that I have to use are axial vorticity eigenfunctions. Okay. So now I am going to just use the same identity. I am going to write omega z of y prime as delta of y prime minus yc times omega z naught of yc. Okay. So these are the axial vorticity eigenfunctions, the amplitude of the eigenfunctions. Okay. And I have expressed my initial condition as a superposition of over the axial vorticity eigenfunctions, which are delta functions in omega z, and over the jet modes, which are the delta functions in uz. Okay. So this is an arbitrary three-dimensional velocity field which is independent of z, expressed as a superposition of the two continuous spectrum eigenmode families. Okay. Now why have I taken this trouble? Because once you write it in this form, and I just repeat it here, so this is the same thing. These are the axial vorticity eigenfunctions whose superposition forms the x and y components. The z velocity eigenfunctions, which forms an arbitrary z component of the field. Once I have it in this form, I know how each eigenfunction behaves. Each eigenfunction propagates with the velocity at yc. So I have the initial field. Now I can readily write the velocity at time t by just adding a complex exponential there. That complex exponential corresponds to propagation with u at yc, the velocity, base state velocity at yc. The base state velocity at yc is just yc because this is Couette flow. Remember, u of y is just y. So once I go through these steps to write it as a superposition of modes, I can immediately obtain the velocity field for any arbitrary time as a superposition of those eigenfunctions. Okay? And this is therefore the solution to the initial value problem. Okay, so the velocity profile where any arbitrary velocity field which is independent of z evolves in this manner in terms of the two continuous spectrum modes. So this is basically the solution of Couette flow for two-dimensional perturbations. Okay. It's going to show an algebraic decay. Yeah, because they are going to be sheared, they will be eventually out of phase with each other. Okay, so I'm going to go to the next level now. We'll consider pipe-Poiseuille flow. And remember, the analog of two-dimensional perturbations here is perturbations independent of the azimuthal angle. So we are going to consider axisymmetric perturbations. Okay, so here we are going to look at again fields that propagate as waves along the axial direction. So instead of x, we now have z, which is the axial coordinate. Okay, so they are independent of theta, so the amplitudes of these waves can only be functions of r. Okay, and I've written 3 of those components: uz, ur, and u theta, the 3 components. This is the continuity equation, which means that if you know one of the velocity fields, you know the other from the continuity equation. Okay, and the analog of omega z would be the azimuthal component of the vorticity. Okay, so an axisymmetric flow field only has the phi or theta component of vorticity, which here I have written it in terms of u hat r. Okay, so this is, we had written there that omega z was d squared minus k squared times u hat of y. This relation is the exact analog of that for cylindrical coordinates. Okay. Okay, and so for instance, if we find omega theta to be a delta function, and we will, okay, then u hat r can again be integrated in terms of the Green's function for this equation. This is the modified Bessel equation. Okay, so you can calculate the Green's function of that. Okay. So now when you do the entire analysis and write the analog, so let me just write what the equation was here for the 2D linear flow, Couette flow. Okay, so this was the general Rayleigh equation. For Couette flow, u double prime was 0. So omega z and u hat z satisfied the same equation. Okay. Notice that u hat z, even for a nonlinear flow, still satisfies the same equation. Okay, but omega hat z is more complicated. So now I want you to look at this system. It is the exact analog of that. Okay, the analog of this equation there, the nonlinear shearing flow. Instead of that, I now have this equation. I have y replaced by r. Okay, c is still there. Omega hat z is replaced by omega hat theta. Now instead of u double prime, I have both u double prime and u prime appearing in this combination. Okay, and instead of u hat y, the normal velocity, I now have the radial velocity. Okay, and this equation is exactly identical. Instead of uz, I have u theta. Okay. So now these are the equations which therefore govern the axisymmetric perturbations. And so I could look for the Couette flow analog. You know, do these equations have a simpler limiting flow, where for Couette flow this disappears. Okay, they would disappear when I have u double prime minus u prime by r will equal 0. Okay, can anyone tell me what flow that is? Okay. So it turns out surprisingly that the analog of Couette flow is in fact pi Poiseuille flow. Okay. So you would think, based on the nature of the velocity profile, that channel flow and pi Poiseuille flow are quite similar, but in terms of behavior of inviscid perturbations, pi Poiseuille flow is exactly like Couette flow rather than plain Poiseuille flow. Okay. So for pi Poiseuille flow alone, this factor would be 0, when we would get exactly the Couette like equations, which are these. Okay, and therefore we would again obtain 2 modes. Okay, so that mode will give us the delta functions in omega hat theta. Okay, and knowing omega hat theta, remember I can derive the radial velocity as a Green's function. That differential operator was the modified Bessel operator, and therefore you have a closed form expression for the Green's function. uz can be derived from the continuity equation, and u theta is identically 0. So this is an axisymmetric velocity field without any swirl. Okay. Now this is a pure swirl eigenmode. This omega theta is 0, u hat theta is just a delta function like uz. Okay. So we have the exact analog of Couette flow for pi Poiseuille flow. Okay. So now we could go through the same exercise again and solved an initial value problem for pipe Poiseuille flow with an arbitrary velocity field for axisymmetric perturbations. Okay, so let's go through that. So that's the initial velocity field. Now instead of x, y, and z, you have r, theta, and z components. Okay. So again, I write them as a Fourier expansion in the z coordinate. So these are the Fourier amplitudes of r, theta, and z. The next step, of course, is to write that theta amplitude as an integral over delta functions, because remember, the u theta eigenfunctions are the delta eigenfunctions. Okay, so this accomplishes the expressing the swirl, an arbitrary initial swirl, in terms of the elementary swirl eigenfunctions. Okay, and then I have these remaining. So what I do next is write ur in terms of the Green's function convoluted with the omega theta vorticity field. Just as for the plane Couette flow, I can write the omega theta vorticity field as an integral of delta functions. Okay, and this expression here is now my initial velocity field expressed as a superposition of two families of inviscid singular eigenmodes. Okay, those are the jet eigenmodes. So here they will be azimuthal jets. Okay, so they will be running along a cylinder, and but otherwise they are exactly similar. And of course, once we have the superposition, like for plane Couette flow, the generalization to finite time is immediate. I just add the complex exponentials. Okay, so that's the initial velocity decomposed into eigenmodes. I had the complex velocity, complex exponentials. Remember, the only difference is that in the parallel flow case, the exponentials general form was this, because the vortex sheet propagated with the base state velocity at yc, and for Couette flow, u of yc was just yc. So I added these exponentials to obtain the time dependent velocity field. Okay. Now here I have the analog as rc instead of yc, and u of rc is the pi Poiseuille profile, and therefore I should add okay, which I do. You can see that those are the complex exponentials, and once I do that, I obtain the time dependent evolution of an arbitrary axisymmetric velocity field with swirl. Okay. Okay. Now, well, maybe this is the last problem that we'll take up. Okay. So this is a different flow. So in those cases, both were parallel flows. Now we are going to consider a base state swirling flow, which is the Rankine vortex. Okay. So how does the Rankine vortex look like? Well, it has a cylindrical column within which fluid rotates as a solid body, and outside the flow is irrotational. Okay. So if I talk about the base state velocity field, the base state velocity field only has one component along the theta direction. That component varies linearly with r within this cylinder up to the radius, and then decays like 1 by r. So if I ask for the angular velocity profile, the angular velocity is of course just a constant inside that cylinder. It should decay like 1 by r squared outside. Okay. So I could write the analog of the vorticity dynamics here. So here it's again the advection and the unsteady term. The advection is along the azimuth. So the advection is in the theta direction. That is the inhomogeneity in the base state vorticity field, which is convected along the normal direction. Normal to the azimuth is the radial direction. Okay. I am considering the inviscid dynamics, so I will neglect the viscous diffusion. Okay. Okay. So before we go and analyze the continuous spectrum, it's just worth seeing what else is there, because unlike pi Poiseuille, so both the previous problems that we analyzed, pi Poiseuille flow and plane Couette flow, the spectrum was purely continuous. There were no discrete modes. That's not the case with the Rankine vortex. There are discrete modes, in fact an infinite number of them. Okay, and they were found long back by Kelvin. Okay. So let's just briefly look at what the discrete modes are before we go to the continuous spectrum. Okay. So now discrete modes of course imply oscillations of the vortex column. Okay. Now one question to ask is, why does the vortex column oscillate? And the oscillation is because of the Coriolis force. Okay, so if we imagine the vortex column to come out of the page and we consider a ring of fluid, okay, let's suppose at a certain instant the ring is expanding radially, then the Coriolis force will actually, if the angular velocity points out of the plane as it does, okay, it will cause these velocity vectors to turn around and then eventually move along a circle. And therefore, the ring first expands. As the velocity vectors turn away from the radial direction, the expansion slows down. At a certain point, the velocity vectors are exactly azimuthal. The expansion stops. The velocity vectors point radially inward, and the fluid ring comes in below, again oscillates, and so on. So the Coriolis forces give a mechanism for oscillation, and these are the oscillations that are the discrete modes of the Rankine vortex. Okay. So like I said, solid body rotation leads to the presence of Coriolis forces, and the balance of inertia and Coriolis force leads to oscillations. Okay, now, so the vortex column oscillations are known as the Kelvin modes. They are known as Kelvin modes because they were first analyzed by Lord Kelvin in the 1880s. Okay, so long back. And the idea again is to look for a normal mode form. If you are analyzing 2D modes, then you would neglect a variation along the axis, which is the z direction. You would just look for azimuthally varying modes. The full 3D modes would imply an azimuthal wave number, which is m by r, and the axial wave number, which is k. Okay. So now again you have 2D modes which don't vary along the axis, and modes in full 3D, which are the equations that Kelvin solved for the Rankine vortex. And if you look at the solutions, it turns out that for every m, remember for 2D modes there is only one wave number, which is the wave number in the azimuthal direction. So it roughly tells us into how many lobes that circular column deforms into, okay, and how those lobes propagate along the azimuth. Here you could have both an azimuthal variation and an axial modulation of the column radius. Okay. So for 2D modes, for a given azimuthal wave number, there exists only one mode. Okay. But as soon as you go to 3D, there exists an infinite number of modes. Okay. So if you look at the discrete modes, these are the 2D modes, how they look like. So that is m equals 2, okay, where you can see that the circle is deformed into an ellipse, and that ellipse gradually rotates. Here it's a 3-lobed shape, so that's m equals 3, and you have one such mode for every value of m. Okay. So those are the 2D Kelvin modes, and these are the 3D Kelvin modes. So when you have an axisymmetric oscillation, where the cross section all along is circular, those are the sausaging modes, where m is 0 but k is finite. You can have the bending modes for m equals 1, m equals 2, and so on. Okay. So if you look at the dispersion relation for the Kelvin modes, it looks like this. Okay. So what is being plotted here is the modal frequency versus the axial wave number. Okay. K is 0 is here, so this is the 2D line, and you go to increasingly 3D modes as you move away. Okay. So I've just drawn a finite number of curves. So m omega is the oscillation at the core angular frequency. So omega is the angular frequency in this core, and m omega would be the frequency where an m-lobed oscillation rotates with angular velocity omega. So this is plotted in this manner because there are modes that propagate faster than the core and modes that propagate slower than the core. The faster propagating modes are called the co-grade modes. The slower propagating modes, for obvious reasons, are called the retrograde modes. Okay? And while I have drawn only 4 curves here and 5 curves here, there are actually an infinite number of curves here. Okay? So if you take any finite value of k, then at that finite value of k, there are an infinite number of discrete modes. Okay? Okay, so there are an infinite number of oscillations for any finite k, 3-dimensional oscillations. But as k approaches 0, all these oscillations collapse into the core frequency, but there is one retrograde oscillation that survives and goes to a limit that is not the core frequency. That is the 1 2D mode. Okay? So again, an infinite number of 3-dimensional oscillations, but only one 2D oscillation. Okay? So if you are worried about the discrete spectrum has one mode for k equals 0, but has an infinite number of modes for any finite k. Okay? Right, and I have plotted it for a particular m, but the picture looks the same for all non-zero values of m. Okay? The range of frequencies just goes from m minus 2 to m plus 2 times omega. Okay? Now, of course, there is a discrete mode. In the 2D case, it's obvious that there is one mode, and you certainly can't have one mode act as a basis. Okay? But so why do we need a continuous spectrum in this case? Well, we need a continuous spectrum because the Kelvin modes physically denote oscillations of the vortex column. Okay? So they only contain vorticity within the core or at the edge of the core. They don't have vorticity outside the core. Okay? So now a relevant question that's attracted a lot of attention recently is, how does a vortex column respond to turbulence outside its core? Okay? Now turbulence is of course a patch of vorticity, okay, but outside the core, and since that vorticity is outside the core, you cannot represent it in terms of Kelvin modes which only have vorticity inside the core. So you need something more, and that something more is precisely the continuous spectrum. Okay? So despite there being an infinite number of oscillations, you still need the continuous spectrum because those discrete modes only contain vorticity within the core. Okay? Right. So like I said, you need additional modes with vorticity outside the core, and it is the continuous spectrum modes that have vorticity outside the core. Okay, so I just drew these continuous spectrum, this discrete modes. These are the Kelvin modes. So remember that this is a 2D oscillation with m equals 2, elliptical core rotating. That is m equals 4. Okay. So I have drawn them like this because if you ask for the perturbation vorticity associated with the Kelvin discrete mode, then the vorticity is located right at the edge of the column. Okay. So the vorticity associated with the 2D discrete mode is a vortex sheet that surrounds the column. Okay. And since it's only located at the edge of the column, there is no vorticity outside, and you cannot represent the vorticity outside. And then you ask for, what do the continuous spectrum modes look like? Well, they look pretty much like the Kelvin mode as far as that vortex sheet is concerned, but it turns out that there is a second vortex sheet in the outer region. Okay, so these are the discrete spectrum modes in 2D with just a single vortex sheet around the edge of the core. These are the continuous spectrum modes with a pair of vortex sheet. That inner vortex sheet is just like the original Kelvin mode vortex sheet, but the outer vortex sheet is like the vortex sheet we encountered in plane Couette and pi Poiseuille flow. So remember, there the vortex sheet in plane Couette flow was parallel. It propagated with the flow, which was parallel. In this case, the vortex sheet is cylindrical and the flow is azimuthal, so the cylinder rotates about its axis. Okay? So both these vortex sheets rotate with a common angular frequency, and that is the 2D continuous spectrum mode. Okay, so just briefly, this is the governing Rayleigh equation for the Rankine vortex in 2 dimensions. So it's the analog of whatever we wrote down here. So remember, uy is replaced by ur now. I am only considering 2D modes because I have only one of the wave numbers, m, the azimuthal wave number. And for the discrete wave modes, I equate directly the differential operator to 0. Okay. But for the continuous spectrum mode, I say that that differential operator is in fact a delta function. Instead of delta of u minus c, I have delta of r minus rf, okay, or rc. So this is the cylindrical vortex sheet structure, okay, and I get the amplitude of the vortex sheet here. So this amplitude denotes the strength of that second vortex sheet. Okay. If I normalize the vortex sheet at the core to be unity, then I have a certain amplitude of the second vortex sheet that's denoted by that expression. Okay. And the nice thing is that unlike plane Couette flow and pi Poiseuille flow, this amplitude isn't always non-zero. it equals 0 at a particular value of RF, which is exactly the frequency corresponding to the Kelvin mode. Okay? So you can derive the continuous spectrum modes, and in terms of an amplitude of that vortex sheet, the location at which the amplitude of the vortex sheet equals 0 automatically gives you the discrete mode. Okay? Okay. So the last thing we'll do is construct an initial condition in terms of these modes. Okay? So remember, I'm going to construct a 2D initial condition. Since it's a 2D field, we have only the axial vorticity. So I'm going to represent an arbitrary initial axial vorticity field in terms of the 2D Kelvin modes. Okay? The only in terms of the 2D Kelvin modes and the continuous spectrum mode, the only difficulty is, of course, I have a Kelvin mode. I have to account for the discrete mode. Okay? So here is the structure of the Kelvin mode. So this is just a schematic. That is a base state profile where I have the cylindrical column with constant vorticity, and there is the irrotational flow outside. Okay? So the vorticity is a step function as a function of the radial coordinate. That is the Kelvin mode eigenfunction, where I have only a vortex sheet at the edge of the core. Okay? So remember that there is the edge of the core. That is the axis of the column. So right at the edge of the core, the Kelvin mode has a sharply peaked vorticity eigenfunction. Okay? And I just told you that the continuous spectrum eigenfunctions have two vortex sheets. There is already one at the edge of the core like this, okay, and a second one outside the core. But the sign of the amplitude of the second one depends on where I am as far as the radial coordinate is concerned, and there is a particular location at which the vortex sheet goes to 0, which corresponds to that Kelvin mode. Okay? So the single vortex sheet discrete mode, the twin vortex sheet continuous spectrum modes, all in 2 dimensions. Okay? Okay, so this is a schematic of the initial value problem. I have a vortex column. I have some patch of axial vorticity that I'm going to call turbulence. I want to see how I can represent this vorticity in terms of the continuous spectrum modes. Okay. Okay, so so what I do first is I take this axial vorticity patch, I decompose it into delta functions. This is the same thing that I did for Couette flow. It is just, if that axial vorticity patch is f of r, I just write it as f of r prime times delta of r minus r prime Tr prime. That is my vortex sheet located at r prime, and that is equivalent to really constructing that axial vorticity as a superposition of the second vortex sheets. Okay? So now let's say that I have found the superposition of second vortex sheets that make up that patch. Okay? Now that's not enough, because remember, each of the continuous spectrum modes has another vortex sheet sitting right at the edge of the column. So when I add second vortex sheets, I will have a corresponding vortex sheet contribution at the edge of the core, which was not there in the original problem. But that's okay, because I have a discrete mode with only a vortex sheet there. So I first add all the continuous spectrum modes to represent this, get an additional contribution here, but then add the discrete mode with the opposite sign at the edge of the core and cancel out that contribution and get my initial value problem. Okay? So here too, although I have not written down the math, it's more complicated, you can represent physically an arbitrary axial vorticity field in terms of the continuous spectrum and the single discrete mode. Okay? Now, I think it's a good point to end here, because I don't have enough time, but what I can tell you is that you can do the same thing in 3 dimensions. In 3 dimensions, just like pipe flow and plane Couette flow, there exists 2 continuous spectrum families for the Rankine vortex. And when you include both continuous spectrum families, you can generate a 3-dimensional vorticity field as a superposition of the 2 continuous spectrum families and the infinite number of discrete modes. Okay? You need the infinite number of discrete modes still. Okay? And this is Rankine vortex in 3 dimensions. You can also go to Couette flow in 3 dimensions and Poiseuille flow in 3 dimensions, but those become more complicated, although it can be done. Okay? So I hope that these elementary problems gave you an idea of what the continuous spectrum eigenfunctions look like and how you can combine them to represent an arbitrary velocity field, even when there are no normal or discrete mode eigenfunctions. Okay? Thank you. at the level of a single eigenmode. But if you consider a superposition of eigenmodes, that will only be weakly sensitive to the vorticity at large R. So the idea of the continuous spectrum eigenmodes is not to interpret them as individual elements, but use them as basis to form a superposition. That superposition won't be sensitive to viscosity, provided viscosity is weak. Okay? So the eigenspectrum will look very different once you add viscosity. Obviously, vortex sheets will be smeared out. The axisymmetric Kelvin modes are found. The non-axisymmetric Kelvin modes have a critical layer. So they have a rapidly oscillating part in them. But again, so it's important to remember that you don't interpret the continuous spectrum eigenfunctions by themselves, because I could also say that in all these cases the CS modes are vortex sheets, and I just found that the vortex sheet was unstable. So why am I talking about vortex sheets? They are just tools to construct an appropriate superposition. No, for a bounded Couette flow, OS doesn't have a continuous spectrum, only discrete spectrum. Yeah, any bounded OS flow will not have a continuous spectrum. The Blasius boundary layer will. So we have done that in that paper. So there is a non-trivial relationship. So there is not a one-to-one correspondence between an inviscid CS mode and a viscous eigenfunction. So an infinite number of viscous eigenfunctions will superpose to form a single CS mode, okay? Which is why it is in fact easier to look at CS modes at large RE rather than viscous eigenfunctions. So I didn't understand your question. We'll go there. So, right. The continuous spectrum modes themselves have streak-like structures, though they are singular. The viscous continuous spectrum modes, not the inviscid continuous spectrum modes. So the inviscid continuous spectrum modes, I spoke about jets, right? There will be streamwise jets, which can be superposed to construct a streamwise streak. Okay? So in that sense, unlike the discrete modes, the continuous spectrum modes have a natural span-wise structure that emerges. I spoke only about two-dimensional perturbations. But when you go to 3 dimensions, the jets turn and then eventually point in the streamwise direction. So you can construct both streamwise counter-rotating vortices and streamwise jets from these modes. So did I answer your? Did you? Yeah. So I forget it. So what is the name you mentioned? Yeah, I forget. I'm sorry, I forget. I should have put the reference. I now forget.
Yeah. So what they did super eigenvalue is just having interaction of discrete and continuous spectrum, and we'll be able to get this scenario. My question was, and that is solving ways.
So you can get streamwise streaks and counter-rotating vortices from a purely continuous spectrum in Couette flow or in Poiseuille flow and so on. Because there is no discrete spectrum. Okay.
So once you showed 4, even before that, I think 4 discrete.
Yeah. That. Yeah. Well, it was intended as a general description. So if you have a velocity field with two inflection points, there will be a mode corresponding, pair of modes corresponding to each inflection point. Okay? Yeah. So I didn't literally show a picture with two inflection points. Yeah, that velocity profile will only have two modes.